This is a look at the panhandle of Nebraska, along with some of the most likely witnesses of the last total solar eclipse here. The year was 1834. On August 21st, 2017, the panhandle of Nebraska will experience a total solar eclipse. It will be the third time such an event has occurred in the last 2,000 years. So what is a total solar eclipse, and why are they so rare? Solar eclipses can occur only at new moon, when the moon is between the Earth and the Sun. But not every new moon produces an eclipse. The moon's orbit is slightly tilted, and as seen in this animation, the tilt causes the moon's shadow to miss the Earth during most new moons, about 5 out of 6 in fact. As the Earth-Moon system orbits the Sun throughout the year, the moon's orbital tilt changes direction relative to the Sun. Sometimes the upside of the orbit is facing the Sun, and sometimes the downside. Twice a year, for about a month, what's facing the Sun is the line dividing the up and down sides, the line of nodes. This is the intersection of the Earth-Moon plane and the ecliptic, or Earth-Sun plane. A solar eclipse can only occur at a new moon that falls within one of these month-long eclipse seasons. That's when the moon is close enough to the ecliptic to actually come between the Earth and the Sun. Just as each new moon is incapable of causing a solar eclipse, not all solar eclipses are total. Some are called annular eclipses. The moon's orbit is elliptical, not circular, so for part of its orbit, the moon is too far away for its disk to completely cover the disk of the Sun. When the moon is centered over the Sun, it leaves a bright outer edge exposed, creating a ring of fire or annulus around the moon, hence the name annular eclipse. We can see an example of this taken by the Curiosity rover on Mars. Here the moon Phobos transits the Sun, casting its shadow on Curiosity. As you can see, Phobos is much too small to cover the disk of the Sun. Its shape is also very irregular. Now that we know the circumstances of a total solar eclipse, let's take a look at our August 21st eclipse. The moon's shadow can be divided into areas called the umbra and the penumbra. Within the penumbra, the Sun is only partially blocked, and observers experience a partial eclipse. The much smaller umbra lies at the very center of the shadow cone, and anyone there sees the moon entirely cover the Sun in a total solar eclipse. In this animation, the umbra is the small black oval. The red streak behind this oval is the path of totality. Anyone within this path will see a total eclipse when the umbra passes over them. The much larger shaded bullseye pattern represents the penumbra. Steps in the shading denote different percentage of Sun coverage or eclipse magnitude at levels of 90, 75, 50, and 25%. The yellow and orange contours map the path of the penumbra. The outermost yellow contour is the edge of the penumbra path. Outside this limit, no part of the Sun is covered by the moon. The numbers in the lower left corner give the latitude and longitude of the center of the umbra as it moves eastward, along with the altitude of the Sun above the horizon at that point. Also shown is the duration of totality. For anyone standing at the center point, this is how long the total solar eclipse will last. Note that the duration varies from just 2 minutes on the west coast to 2 minutes and 40 seconds east of the Mississippi River. This animation closely follows the moon's umbra shadow as it passes over the United States during the August 21st eclipse. Through the use of a number of NASA datasets, notably the global elevation maps from the Lunar Reconnaissance Orbiter, The shape and location of the shadow is depicted with unprecedented accuracy. During the eclipse, the moon's umbral shadow will fly across the United States from Oregon to South Carolina in a little over 90 minutes. The path of this shadow, the path of totality, is where observers will see the moon completely cover the sun. People traveling to see totality, likely numbering in the millions for this eclipse, will rely on maps that show predicted location of this path. In keeping with their paper and pencil origins, traditional eclipse calculations pretend that all observers are at sea level and the moon is a smooth sphere centered on its center of mass. Reasonably accurate maps are drawn based on those simplifying assumptions. Those who want greater accuracy are usually referred to elevation tables in plots of the lunar limb. You might think that calculating the circumstances of an eclipse would be, if not easy, then at least precise. If you do the math correctly, you'd expect to get exactly the same answers as everyone else. But the universe is more subtle than that. The Earth is neither smooth nor perfectly spherical, nor does it rotate at a perfectly constant, predictable speed. The moon isn't smooth either, which means that the shadow it casts isn't a simple circle, and our knowledge of the size of the sun is uncertain by a factor of about 0.2%, enough to affect the duration of totality by several seconds. Everyone who performs these calculations will make certain choices to simplify the math or to precisely define an imperfectly known number. The choices often depend on the goals and the computing resources of the calculator, and as you'd expect, the results will differ slightly. You can get quite good results with a relatively simple approach, but it sometimes takes an enormous effort to get only a slightly better answer. These very accurate maps are the work of data visualizer Ernie Wright. Let's listen as he explains how they were made.
What we're talking about is several visualizations of the path of the moon's shadow during the eclipse in 2017. Everything in it is driven by the data. So the color of the ground, the position of the path of totality, the lighting from the sun angle, all of those are things that are based on data. A lot of NASA products were used to create this visualization. I used the Lunar Reconnaissance Orbiter, the laser altimetry data from that, which gives us a digital map of the elevations on the moon. For the Earth, I used something called SRTM. This was a radar that was flown on the space shuttle. For the positions of the Earth, the moon, and the sun, I used a JPL ephemeris. An ephemeris is just a list of positions, but it's the most accurate tabulation of those positions. This visualization is unique because it shows the effect of both the irregular edge of the moon, the limb of the moon we call it, and the elevation of the observer. Now, we've known for a long time that the elevation of the observer affects where the shadow is. We've also known that the mountains and the valleys along the edge of the moon affect the shadow. So you may have seen on eclipse maps in the past that the image of the umbra, that shape of the shadow on the Earth, is drawn as a smooth oval. But we know that the moon isn't smooth. Around the edge of the moon, we have these sort of jagged peaks and valleys. And a peak can block the sun a little bit earlier than you thought, and a valley can let the sun in a few seconds longer than you thought. The combined effect of these peaks and valleys is to create a shape that's not really an oval, it's more like a polygon. But it hasn't actually been seen in exactly this way before, where we calculate those circumstances for every point on the map and draw that shape. Totality is that 2 minutes or 2.5 minutes when the moon completely covers the sun. The sudden darkness of totality is just something that a lot of people can't compare to anything else. I love the idea that I'm giving this kind of map to other people, and especially that it's more detailed and more accurate so that people are actually in the right place to see it.